So I'm very happy to be here. I saw the website of the Hadamard Matrices conference some time ago already, and I said that's really the right place for me to go because I want to tell you sort of my own path to Hadamard Matrices. So I did quantum algorithms and quantum information, and at some point I decided that it seems like Hadamard matrices must be really useful for quantum algorithms, and I started reading all kinds of papers about Hadamard matrices and books, and some of the, now finally when I come here, I can put faces on some of the names that I see in the papers. And so I basically wanted to tell you, so I'm not telling any result in basically this talk, but I want to tell you is about a problem or sort of like a way of thinking that I think is useful, and especially for this audience, because it's basically, I think for the Hadamard people, it's interesting that they can apply the Hadamard matrices to the quantum algorithms. And for the quantum people, I think it's interesting that they can, use some Hadamard matrices to make quantum algorithms. So I think it's interesting for both sides. And so, yeah, so I want to combine these two things together. And so here you also see a picture. So this is a quantum circuit of a quantum Fourier transform. And so you can see there is lots of these H. So these are 2 by 2 small Hadamard matrices. And actually the whole circuit together, it implements Fourier transform, which is also an Hadamard matrix. And so basically this 2 by 2 matrix here, it appears in many quantum algorithms, and so it's somehow very useful. And also Fourier transform appears in many algorithms. It's also very useful. But there are many other Hadamard matrices, like this big one, 92 by 92, and somehow they are not really used in quantum algorithms. And I feel like these, the 2 by 2 one and Fourier transform are overrepresented, and there might be more potential for the other ones. Okay, so I need to tell you basically about two things. I want to talk about quantum algorithms and about Hadamard matrices and how to combine them. And I will talk about specific type of algorithms. They are called quantum query algorithms. So what is a query algorithm? So let's just start with a classical query algorithm. So basically, you want to determine some property of input data by looking at just one bit at a time of this data. And so the model is that we pay basically per access, and we don't pay for the computation time. So it's like you can imagine maybe somebody sends you these bits and it's very expensive to send them, or maybe there's some subroutine that produces them and it's very expensive to run the subroutine, but we only care about how many bits we access. Okay? And so that's the complexity, how many bits you need to see to decide some property of the data. So for example, here's a very simple example. You are promised that you have some input string, which is either 3 zeros or 3 ones, and you want to determine which one it is. So then the complexity of this problem is just 1, because if you look at any of these bits, then you know, like if you see 0, you know it must be 3 zeros, or if you see 1, you know it must be 3 ones. Okay, so here's another more complicated example. So let's say you have an n-bit string, and you have no promise it can be any string, and you want to know what's the parity of this string, right? So now in this case, if you ask the bits, you can ask them, and even if you ask n-1 bits, you have a kind of like, some guess what the parity might be, but you still don't know the last bit. And actually the last bit completely determines what the parity is. So basically, in this case, the complexity is n because you really need to know all the bits before you can decide the problem. Okay, and so now in this talk, I will use this, it will be my running example. So we want to know, so imagine you have this kind of matrix, so plus minus ones, made out of these I don't know how to pronounce the...
Let's say pretzels.
Yeah, okay, so these 2 types of pretzels. And so you're promised that these, that somebody picks one of these rows of these pretzels, and you have to guess which row it is. And you can ask the entry. So basically, you have these x1, x2, x3, and so you can ask, I want to know what is the, for example, here in this case, a good strategy is to ask what is the bit x3. Yeah. So let's say if the answer is 0, it must be one of the first 2 rows, and if it's 1, it must be one of the last 2 rows. So that lets you cut down by 2. And then let's say it was, the first 2 rows, then you can ask x2, and then it lets you cut down again by 2. Okay? So basically, if you ask x3 and then x2, then you know which row the person had in mind. Okay? And actually, this will be the running example, or like somehow the generalization of this example will be sort of the main thing I want to tell. And actually, the main idea I want to explain is actually very simple, but then I think it's the question is how to apply it basically. Okay, so in this case, the complexity is 2. All right, so I will need to explain some quantum computing. So I need just very basic things. So many already know it, but so basically in quantum computing, you have a state of the quantum computer, which is just a unit vector in n-dimensional complex vector space. the operations are described by unitary matrices, and intuitively they're just rotating this state in some way, and they are reversible because you can always rotate back. And so then you need to get information out at the end of computation, and we will need only a very special type of readout operation, which is basically if you manage to rotate your state towards one of the standard basis states, then when you read out information, then you just get the number of that state. Okay, so basically, if you get a state of this form, whatever the state is, and you ask the give me the answer as just measure this state, then the answer is just k, is the position where you have collected all this. Okay, so this is kind of all you need to know about quantum computing. All right, so that's the very basics of quantum computing. Okay, so now the question is, how do you input the data in your quantum computer? So this was how you compute and how you get the data out, but you need to get the data in. Okay, and so this getting this data in will be sort of this process of accessing this data. Like I was giving these examples where you query these bits, and so in one case, so there are sort of two different ways to do it, but the simplest one is this one. So you basically, let's say you have some n-bit string, and you want to access this string, you will just apply the diagonal matrix that has plus minus 1s on the diagonal. And so this matrix is clearly unitary, so it's allowed. And this you just basically convert this bit string into a string of plus minus 1s. And you can generalize this. Maybe you're accessing some things that are not bits, but it have values, modulo b. Then you would just put the root of unity on a diagram. Okay, and this is called oracle. This is sort of the operation that gives you access to the data. And so maybe one thing that's not so clear is that when you apply this, like which bit are you asking? Because like in these classical examples, I was asking bit number 3 or bit number 2, but in this case you just apply this operation. And so somehow here the idea is that which bit is queried depends on the state in which you apply. So like if your state has amplitudes, let's say it has zeros everywhere, but then it has like 2 amplitudes on some specific positions. Then when you apply this operation, you learn information about like those 2 bits basically. Okay. And so basically what you're querying depends on the state that you have, but the operation is always the same. You just apply this diagram. All right, and so this basically together defines the model. So we use this matrix to access the data, and then we use some free unitaries that we can do, and then we read out information. And the complexity of the algorithm is how many times you apply this whole operation, this oracle that accesses the data. Okay, so and now what I will explain is the simplest possible quantum algorithm. And so yeah, I'm sorry for the quantum people who already seen this, but I just want to kind of for the Hadamard people to get the idea. And so basically this is the first algorithm ever. So it's by Deutsch in 85. And actually, so this algorithm, it's sort of increasingly inspired more complicated algorithms that eventually led to Shor's algorithm for factoring. And so somehow, even though this algorithm is extremely simple, I think there are many different ways to look at it, and there are many things you can still learn from it. Okay, so the way this algorithm works is you start with a state that just has the uniform superposition. So then you apply this oracle, you access the data. So I'm not telling yet what the problem is this algorithm solves. I just say what the algorithm does. Okay, so it accesses this 2-bit string. So what does it mean? It means that you just multiply your this is your state. You just multiply it by this diagonal matrix, and you just get this state has these plus minus 1s. So this uniform superposition with some plus minus 1 amplitudes. And then you apply the Hadamard matrix. So this is where the Hadamard matrix enters the picture. Okay, and then you just apply it, and then you read out the answer. So let's see how does this work. So there are 4 possible combinations of these bit strings, and then there are 4 possible states that you might get. They just all possible combinations of plus minus 1s. And okay, so now now we need to understand the step 3. That's the most complicated step. Okay, so and to understand the step, we just need to know this is another Hadamard matrix. Namely, if you multiply this itself, so it's in this case it's symmetric, then you get the identity matrix. Okay. So now if we just want to analyze what happens here, so if you apply the Hadamard matrix on this one, then because this state is just one of the columns of the Hadamard matrix, you will end up getting this vector. So you get the first standard base vector. Okay, so now here you're applying essentially, you're applying this operation, this Hadamard matrix, onto the second column. So you're just going to get the second column here, which is the second standard base vector. Okay, and the other cases are similar, except that there is just a minus sign in front of the vector compared to here. And there's a big minus sign in front compared to here. So you just get these 2 standard base vectors with some minus signs. Okay. And so now, the readout that I define is just you basically you're asking which standard base vector it is. And so I label them from 0. So basically, in the first case, the answer is 0, then the answer is 1. And we just ignore this global phase. Here the answer is 1, here the answer is 0. Okay. And so basically, this is the information that the algorithm computes. It just, basically given this 2-bit string x, which is given here, it produces this as the output. And it accesses the string only once, because we apply this oracle operation only once. Okay, and so what is this? What is this function it computes? You can just write it down like this. And so then you can ask, well, what does this mean? Like, how can you describe this function? How can you interpret what the algorithm does? Okay, so there are several ways you can do this. You can say, okay, we're accessing a 2-bit string. Now let us decide, is this string 0, 0, 1, 1, or is it one of the others? Is it in this set or that set? One way you can interpret it. You can say it lets you decide whether the 2 bits are equal. So in this case, they're equal, and in the middle case, they're different. You can say that it adds the 2 bits, or it computes the XOR, adds the 2 bits modulo 2. Okay, so that's all fine. But now, so these last two interpretations are a bit unusual. So you can say it computes the derivative of any function modulo 2. So I'll explain what this is. It's sort of not obvious. I knew about the algorithm for a long time on it. I didn't know anything about this. And so the main message of my talk is you can also think of it as identifying a role of another matrix. Okay? So I will explain these last two. I will explain them next in more detail. Okay, so and by the way, so of course, the interesting thing is that you compute this XOR or the parity of the 2-bit string by accessing the input string only once. Right, so like it's obvious, like for classical query algorithm, that you need to really query both bits, but in quantum case you need to query it only once and superposition. And so that was sort of the first illustration that the quantum computers can do something better than classical. So this is the simplest possible illustration of this phenomenon. Okay, so let me explain this derivative idea. So why is this algorithm that I explained computing the derivative of some function, which just doesn't seem like anything like that. Okay, so I will label my bit string, I will just call it x0, x1 now. And you can think of it as a function. It's just a function. So this bit string is just a function that given the position of the string just gives you which bit you're accessing. And I will replace, instead of writing x0, x1, I will just write f of 0 and f of 1. So you can think of, instead of querying bits, you have like a subroutine that I call f, and you just, you call this subroutine and it gives you the answer. You kind of evaluate on some function. Just kind of changing perspective. Okay, so now there are, so these are all possible functions you can have from a single bit to a single bit. Right? So basically you just need to know what's the value of the function on 0 and what's the value of the function of 1. And there's all possible 4 combinations. And you can write just the 4 functions. And the first one is just, the function is always 0. The last one is it's always 1. So these are the constant functions. And this is the linear function. It just returns the inputs. So on 0, it gives 0, and it gives 1. And this is the sort of the negation function. You just add 1 and 1 to. So these are the 4 functions. And in fact, you can see that actually these functions are all of the form like this. So basically any function from a single bit to a single bit is linear, or affine, to be more precise. So it's just given by these 2 parameters, A and B. And so now, what the quantum algorithm does, it was evaluating the sum of these 2 bits, or in this case, the sum of the 2 function values. Okay? And so these are the functions because it's affine. So if you compute this, we just have b plus a plus b, and because we work modulo 2, then this is equal to a. Okay? And so the a is the slope of the function. So you can think of this is as computing derivative of this linear function. And so this might seem, okay, it's a very convoluted way of interpreting the algorithm, but it's a valid way, and there's a sense in which you can generalize this. And I will explain how you can generalize this in a less primitive example. Okay, so this was sort of one of these interpretations, and so here is another interpretation that I proposed, is that you can think of this Deutsch algorithm, so the most basic quantum algorithm, as guessing a row of an Hadamard matrix. Okay, so let's say we take a 2 by 2 Hadamard matrix, and you can even throw in some phase in front. You can sort of allow to multiply it by -1 if you want. Okay, and the computational problem is that you have access to this. So somebody picks a row of this matrix, and you need to guess which row it is. And so it could be either the first or the second row, but also you can have this phase in front, and so there's like 4 possibilities. Okay? And so basically this oracle that accesses the input, it can be basically any any diagonal matrix with plus minus ones, because here, if you add the minus sign, you can get all four combinations. Okay, so and now this was the function that the oracle was the algorithm was computing. So it was just mapping when two things are equal, it was producing plus, and when the two things are different, it's producing minus. Okay? And so you can just establish a correspondence. Then when the two things are equal, then it was definitely this first row, when potentially there was some sign, and when the two entries are different, then it has to be the second row. Okay? So you can think of this algorithm as identifying a row of Hadamard matrix. You can think it's like a game. Somebody chooses this row, and you can access it one bit at a time, and you need to guess which row it is. And and this what it shows is with one guess you can guess this row. All right. So now this this is how the Hadamard matrix enters the picture, and now I want to sort of I want to strengthen this claim, and I want to kind of make a generalization out of this observation. Okay, so let's just define what I will call the guess the Hadamard row problem. So somebody chooses an n by n Hadamard matrix, and for simplicity it's plus minus one matrix, but it can also be lots of Hadamard matrix or just any complex Hadamard matrix. Okay, so now so let's say it's just a plus minus one matrix. Then you can say, well, every row of this matrix is just encoding some n-bit string. And and so somebody basically picks this row when you need to guess. So you can access this the entries of this row one by one, and you need to decide which row it is. Okay, and we want to do it with a single query. And the algorithm is what I explained before. This Deutsch algorithm we just scale it up. So you just start with this uniform superposition, then you apply this oracle. So it's a diagonal matrix that encodes the entries of the row, and of course you will just get a state whose amplitudes are just equal to the plus minus one combination of that row, and then you just apply the Hadamard matrix itself. And because the rows so the Hadamard matrix itself, once you normalize it appropriately, it's an integral operation, so it's something you can do in principle on quantum computers. And of course, once you do it, then what's going to happen is that because the rows are orthogonal and you have already one row sitting there, you will just get one of the standard base vectors. And then when you read out the answer, you will see which row it was. Okay? So this is like a generalization of this Deutsch algorithm, and it's kind of specifically tailored to Hadamard matrices because you can run this for any Hadamard matrix. Okay? So here's just an example based on the canonical example in this conference. So let's say you have this 4x4 Hadamard matrix, and somebody chooses this row. So then this oracle that accesses the data will be just this diagonal matrix. You apply it to the all ones vector, and you just get that row literally as your amplitudes. And so now this is your state, and once you apply the Hadamard matrix itself as an operation, then because that specific row is sitting in your state, then what you get is you get one of the standard base vectors, and the position that you get one here is exactly the row that you start. So this is like the main thing. If you get anything out of this talk in this example. Okay, so now. Okay, so is this good for anything, right? Like it's okay, it's like a contrived problem. So now, if you look up any book about quantum algorithms, you will first learn about Deutsch algorithm, about this and that algorithm, and all these initial algorithms are exactly of this form. Basically, you start with some kind of zeros, and then you apply some kind of Hadamard matrix. So usually it's just the 2x2 Hadamard matrix and the qubit. And so this first step just prepares uniform superposition, then you apply the oracle, and then you apply the transform or some small Hadamard 2x2 matrices, and then you measure. So there are many algorithms of this form. So for example, the Deutsch algorithm that I mentioned, so this is just for this 2x2 matrix. So then there's the Deutsch-Joss algorithm, which was like a generalization. It's just the same thing, but for the H tensor n, for the 2x2 matrix, and scaled up n times. And none of these people thought of it this way as guessing some row of an Hadamard matrix, but this is the idea they use. So then there was the version of the Zerani algorithm. Again, it's the same idea with the same matrix. And then there is this algorithm about sort of Hamming distance. I will explain it a little bit later. This is specifically for this small matrix, and then you can take an n tensor power of that. Then there is an algorithm for the shift of Legendre symbol and its generalizations. And that basically used the same idea, but for the Spelling construction that other people must be familiar with. And there's another sort of set of algorithms for hidden shift problem for blend functions. And we heard also a couple of days ago some talks about blend functions. They're also closely related to Hadamard matrices. And so all of these algorithms, they basically are exactly the same type, and they do exactly the same thing, and they just use different Hadamard matrices, and they interpret the result in a different way. And I don't think that anybody has sort of acknowledged this pattern basically in quantum algorithms. And I think these algorithms were just kind of discovered one by one, and people were just trying to use different tricks. But sort of all these tricks, they just fall under the same umbrella. They're just using some Hadamard matrix. And so basically, so what I'm saying, and this was actually formally observed in a PhD thesis of Ashley Montemurro, that there is a correspondence between Hadamard matrices and exact one-query quantum algorithms. So basically, quantum algorithms that make one query and that work exactly. So basically, what I showed you is one direction of this simple observation. So given Hadamard matrix, you can make up this guess the Hadamard row problem, and you can solve it with one query exactly like a quantum computer. And you can also prove the converse direction. It's not too complicated. Basically, given any exact one-query quantum algorithm, it can, use some extra workspace or do something crazy. But in the end, you can sort of massage this algorithm into some standard form, and that standard form, from that you can extract the Hadamard matrix. So basically, there's exact correspondence. And I'm not saying this is a deep result. This is actually a very sort of elementary result, but I think it has sort of important consequences because it means that you could call this conference the conference an exact one-query quantum algorithm, and it would be a valid name because this is the same thing. I just want to basically emphasize that this is not a perspective that people have in the field, and I think it could lead to some new insights. So basically, the main question I want to ask is, can we discover new quantum algorithms by using some ideas of Hadamard matrix theory? So in particular, using other Hadamard matrices. There's like people were classifying Hadamard matrices that had 13 million different kinds. Like in quantum algorithms, we use basically two kinds. We use the 2x2 one, and then we use the Friedrichs form. And there should be more potential for the other ones. So that's what I'm saying. Okay, so now I want to illustrate some example where this kind of philosophy has succeeded, but it's not like basically what I'm saying is nobody has explicitly stated this as sort of like a way of thinking about it, but it has kind of by accident sort of succeeded. So I want to explain this idea of computing gradient. So there's a quantum algorithm for computing gradient, and historically it went through all kinds of sort of developments until it reached this final conclusion, but it really originated from this Deutsch algorithm. And so basically, let me explain the generalization of this Deutsch algorithm, which is called Bernstein-Lazarani. So it's from 1997. So here the problem is as follows. So you have some function which is linear. So it's basically sorry, it's a typo. It maps an ended string to a single bit, and it's just linear function. There is basically some kind of unknown string s, and you just take inner product with your input modulo 2. Okay? And so the goal of the problem is to determine this s. So you can basically have access to this function. It spits out one bit, and it just takes inner product with some unknown bit string, and you want to know what is this bit string. Okay? And so the observation is like, how would you solve this problem? Well, you would just observe that if you take this normal 2x2 Hadamard matrix and you tensor it itself n times, then you can label the rows and columns of this matrix by ended strings, and the entry labeled by string s and x is just -1 to the power s times x. And so it's literally this some row s of this Hadamard matrix just encodes this function. And so now if you want to find out s, you would just play this guessing the Hadamard row this game, basically, right? So this is basically this Bernstein-Lazarani algorithm is just equivalent to guessing the row of this H tensor n form. Okay. Okay, so this was observed like in 1997, and then so it was observed only later that this can be interpreted as computing gradient. So let me explain that. So if you have this linear function where you just take an inner product with some n-bit string that you want to figure out. So the question is now, how can you obtain this s by one query to this function? So sorry, you can obtain using this, what I explained before, you can obtain this s by one query is just guessing the Hadamard row. And it's also easy to see that classically that you need n queries. Like for example, what you can do is you can query it on all standard base inputs, like basically on all strings that have all zeros and then one at all positions. So if you evaluate on such a string where there's one position, I, then you just get si, and you can do this n times, and then you can extract all these symbols. And also what is surprising that like here, like, I think what is kind of counterintuitive while this version was running an algorithm is that you are extracting an n-bit string, but you're accessing data only once. And like sort of, and one accessing data only once, it's sort of modeled by kind of querying one bit, like in a classical case. But in a quantum case, you apply this diagonal transformation, and somehow you end up learning n bits, even though you access data only once. And I mean, there's no cheating. This is like sort of, you can make an argument why this is a reasonable model, but I think this is kind of surprising. And so basically, there's this difference between n and 1. So you need one query quantumly and n queries classically. Okay, and so now you can, of course, easily generalize. You can say, well, instead of having this function 1 to 2, you can just say, well, let's make modulo n. And then instead of this 2 by 2 matrix, this other matrix will just have the Fourier transform, because the Fourier transform has also this product of s and x, sitting there. And so basically, if you are guessing the row of the Fourier transform tensor n, this will be equivalent to finding the gradient of this function. Okay. And and it took like so basically, okay, so this version was running algorithm was known like in 1997, and it took to 2005 to realize that this could really be sort of computing gradient. Like this was before, it was just known as like you have this obscure problem, you want to extract the string S, we don't know what it means or what it's good for. And so basically in 2005 it was observed that you could really think of it as computing gradient, and you can use it to actually compute gradients of real functions. And then it took like 12 more years plus a bit more to kind of fill in all the details and make this rigorous. So basically what you can show is if you have access to a function, like let's say from n real numbers to a single real number, and you want to estimate the gradient of this function, so as a real vector, then if you want to do it with an accuracy epsilon to like 1 more, and then you need to do so many queries to this f. And the point is that classically you need n over epsilon squared queries. And I think so. This is basically sort of like I call this the great success of this philosophy of guessing the Hadamard row, because the problem itself, guessing the Hadamard row, is just very obscure. It doesn't have any clear application. It's not clear what it's good for. It depends on what is the structure of the Hadamard functions. And basically, in a case when you're playing this game for the Fourier transform, then you can reinterpret the problem that's being solved as computing gradient. And that's a useful problem because you can use it for optimization. Like if you're doing some kind of steepest whatever descent, you can you basically need to evaluate the gradient fewer times. So that's very useful. And so basically, the main thing the main problem I want to propose now, are there any other instances of this phenomenon where we can take some other family from our matrices and get a quantum algorithm for some interesting problem? So let me say, okay, so I know another example, which is, I think it's kind of on track, and I don't know if it's so useful, is this summing distance modulo 4. So basically here, you take this 2 by 2 matrix like this, and if you tensor it with it, so basically, so notice first that you can think of the entries of this matrix as computing the distance between the two inputs. So here the two row and column indices are just bits 0 and 1. And so on a diagonal, the distance between the column and row labels is 0, so you can get 1. And on off diagonal, the distance between the two indices is 1, so you can think of it like this. And now if you tensor this matrix n times, then basically how you can think of the entries as measuring the distance modulo 4, because this is the force infinity, between the two input strings. And so basically it's like you supply an n-bit string, and there's some hidden n-bit string that you want to guess, and you get as an answer, how far is your string from the original string modulo 4. And with just one access to such a function, you can figure out what is the hidden string. It's kind of like surprising, but it's not particularly useful. I think I'm running out of time. So, okay, so there's another example that I just made up yesterday, because there was this talk about decoding codes. Like, for example, if you have an Hadamard matrix and you just take the logarithm of it, and basically you just take all the rows of it, and then you add multiples of all ones vector, you can form a code. And there was some example that somebody mentioned yesterday. And again, like if you want to decode this code, it's just guessing in the row of this Hadamard matrix. And if there is a little bit of noise, you could still run the same algorithm, and with high probability, you will probably decode it correctly. And I don't know like what are the implications of this, or is this useful for anybody? But I just want to say, like, I think there's lots of potential to sort of to apply this idea. Okay, I think I will skip all this. Okay, so you guys also know there's all these cross-cyclic matrices, and in this case, you can, instead of guessing the Hadamard row, you can basically say that what you're doing is that you have access to a pulse cycle. So it's a function of two arguments, and one argument is fixed to some unknown value, and you have access to the other argument. You just want to guess the first argument. And again, this is, it's just an instance of the same thing. You can say, well, if this pulse cycle is orthogonal, meaning that there's an Hadamard matrix, then a quantum algorithm can guess this other argument with a single query. And again, this is a very contrived problem, but who knows? If the pulse cycle is nice and has enough structure, maybe this problem is useful. All right, so what's the summary? So we can, so one query is enough to guess the row of any complex Hadamard matrix from a quantum computer. And there are various quantum algorithms that implicitly make use of this, but I don't think this has been explicitly stated as like this is what's actually going on, and let's go dig deeper and try to come up with new algorithms. And normally this guessing the row problem is very contrived, and unless you can interpret it in a different way. And I think this is the difficult part about this approach. It's not clear how to do this interpretation. It took like 12 years to go from this Deutsche algorithm to realize, oh, this is computing gradient, and this is something useful. And this gradient, of course, is the success story of this approach. So open problems. So I think the next question to ask is, well, how about exact two-query algorithms? Like, is there some combinatorial structure there? I haven't thought about this, but I think there might be some structure there as well. Of course, the main questions I want to raise is like, is there some family of, for example, Hadamard matrices for which this guessing the row problem does something useful, where you can interpret something useful? And then, of course, you also need to ask, if you store it classically, if you just access this one bit at a time, how many queries do you need? And you need to beat the classical algorithm, otherwise it's not interesting. And of course, there was also this quote. I don't know if you guys noticed the previous room of the conference. It has this quote above the door. You should always, adopt things. And I don't know if this approach is useful. I'm just kind of throwing it out there. Maybe nothing will come out of it, but I just want to put it out there. All right, so that's all I want to say. So I wanted to maybe relate a little bit to Kraków. So there is this guy, I don't know if you know. I mean, the local people definitely know. So this is like a tradition here apparently in Kraków, that every year on a special date, there is this guy with this funny course who goes on a procession around the town. And it's a very old tradition. You can see, if you look carefully, he has the Hadamard matrix here embroidered on his, decorated horse. And there's another horse also in Kraków, this sculpture, with a horse with 3 legs. And if you look carefully, you can see there's a quantum circuit engraved. And both horses have a problem. This horse has a leg missing. It doesn't have the Hadamard matrix to use. This is actually a fake horse. It's just, so basically we want to combine these two things together. And then we have a proper recommendation. So that's what I want to say.